Okay, welcome everyone. Today is our great pleasure to have Richard Allen as our speaker. Richard is currently a PhD student at MIT. Uh, Although he is still a PhD student, he already has had a very rich experience. As an undergraduate student, he already conducted research on quantum error correction, superconducting qubits, and had some very influential publications with, for example, Google Quantum AI team. And then he went to the University of Oxford as a master student. Also, there he conducted some interesting research on realizing nonlinear anions using quantum circuits. And now, as a PhD student at MIT, he continues doing great work. Today, he's telling us about quantum computing enhanced sensing. Welcome, Richard.
Great. Thanks so much for the very generous introduction and to everybody for coming to the talk. I know it's early for you, late for me. So yeah, thanks for being here. And I'm very excited to share a bit about our recent work on quantum computing enhanced sensing. I hope you'll all find it interesting. So let's see here. So yeah, before we get started in earnest, I'd just like to take a moment to sincerely thank my co-authors on this project, in particular Francisco Machado, who's at the time postdoc at Harvard and now has his own group at Delft in the Netherlands. Ike Trong, who's here at MIT, Robert Huang, who's at Caltech and at the time was visiting MIT, and Soonwon Choi, who's here at MIT. So let's get started. I think we can all agree that right now we're living through, say, a very exciting time for quantum science and technology. And we're witnessing really rapid progress. And in particular, we're witnessing rapid progress on all aspects of the experimental design of our many-body quantum platforms. And with all of this exciting progress, I think it's more important now than ever to ask ourselves the question, what should we do with our quantum devices? Now, there are, of course, many answers to this question, and it would be too ambitious to try and address them all in one talk. But today, I'd like to convince you that one very promising application of quantum technology, and in particular of quantum computers, will be quantum sensing. So let's all get on the same page with respect to quantum sensing. Quantum sensing is at this point responsible for humanity's most advanced measurements of essentially all physical phenomena, ranging from gravitational waves through LIGO to the measurement of time through atomic clocks, the measurement of parameters in fundamental physics, particle physics, magnetic field sensing, and many, many more applications. So the point that I really want to drive home here is that progress in quantum sensing is progress not only towards better quantum science, but towards better science in general. Okay, but before we get started in earnest, let's just take a moment and get our feet wet with the simplest or perhaps most canonical environment in quantum sensing and most canonical example. And that's the problem of detecting just a single qubit magnetic field or detecting a magnetic field with just a single quantum sensor. So the setup is as follows. You have a two-level atom, some spin, which you imagine couples to a magnetic field in, say, the Z basis. And the goal is to estimate the value of the strength of this magnetic field, which we will call B. And one way that you can do this, very simple, is just prepare your qubit in the plus state, so sort of transverse to this field, let it evolve, let it process, and then perform measurements in the computational basis, zeros and ones. And by doing this, you can construct an estimator of B just from the how often you get zeros or ones. And one common figure of merit in quantum sensing is known as the sensitivity, and it's basically the minimum detectable field strength. And for this protocol, the minimum detectable field strength is just going to scale like 1 over the sensing time, 1 over t. And that's just because you need an angle of phase accumulation, which is order 1, in order to detect whether or not the field is present. And that's sort of the fundamental limit for sensing with a single sensor. But often in quantum sensing, we care about what you can do with many sensors. One thing that you can do with many sensors is just let them all evolve one by one under your field and measure them, again, one by one, and then average your results. And if you do this, then your sensitivity improves by a factor of square root of n, and this is known as the standard quantum limit. What a sort of key motivational result in quantum sensing is that this is not the fundamental limit for sensing with n sensor particles. And then in fact, you can do better by preparing your sensors in some crazy entangled state. So in particular for this problem, if you prepare the sensors in a GHZ state, so a superposition of all zeros and all ones, then the entangled state acts sort of like a large effective qubit, which has a collectively enhanced coupling to the magnetic field and processes n times faster. And as a consequence, your sensitivity improves to 1 over n times t, so a full factor of n over the single sensor limit. And this is sometimes known as the Heisenberg limit in quantum metrology. And it really is the fundamental limit for detecting time-independent magnetic field using N-sensor particles. And this is all good and well, and this gap between the standard quantum limit and the Heisenberg limit has motivated many decades of both theoretical and experimental progress in quantum sensing. It's very influential.
Richard, can I ask a question?
Sure, yeah, please.
I actually don't know much about quantum sensing.
Okay.
So, can you intuitively explain why this Heisenberg limit is the fundamental limit? Why does it not depend on how we do the sensing and all other details?
Oh, yeah, that's a great question. It's sort of like a speed limit for how quickly, so there are many perspectives on it. One, I mean, you might notice that it's called the Heisenberg limit. This is perhaps related to Heisenberg uncertainty principle. In fact, it is. You can think of this as the manifestation of energy time uncertainty principle in quantum sensing. The way that I like to think about it is there's sort of a fundamental rate at which you can extract information about this unknown signal. And so it's easier to see in the single sensor case uh, because you're sort of learning information about the field at a rate that's like b. Then if you want to estimate to precision b, then that'll take like 1 over b time and 1 over your rate. And then if you have n sensor particles, you can argue that that rate should be increased by a factor of at most n. And so the sensing time should go down by a factor of at most 1 over n. And yeah, so there are many ways of approaching it, but I like to think of it as like the rate at which you can extract information.
Uh-huh. Uh, and is there a general and rigorous proof of this, which applies to general protocols of sensing?
Yes, there's a rigorous proof. That's very easy.
I see.
Yeah.
Thanks.
No problem. Okay, great. So yeah, but if this part sort of didn't make sense, in fact, you can kind of forget about it because in this talk, we are not going to be talking about standard quantum limit versus Heisenberg limit. In fact, we're going to be asking a different question, whether or not there are other very qualitatively different sources of enhancement in quantum sensing. So by this, I mean qualitatively different than the collective enhancement due to some many-body entangled initial state. Maybe even with, a single sensor, which is exposed to the magnetic field, you can get some sort of advantage in quantum sensing. That's what we're going to explore in today's talk. And the way that we're going to explore this question is by introducing a new paradigm for quantum sensing, which we call quantum computing enhanced sensing. And in this paradigm, we're going to imagine, to contrast it with the conventional paradigm, conventionally, while it might be possible to prepare some entangled input state of all of your sensors, the evolution or the sensing protocol after that time is in some sense like very classical. It's typically like single qubit gates, pre-programmed, very simple. We're going to consider what we call quantum computing enhanced protocols, where in addition to entangled input states, you can also perform quantum controlled gates during the protocol. So you can do entangling gates between your quantum sensors and some small quantum computer. And the question that we want to answer in the setting is really whether or not quantum computing fundamentally can be leveraged to improve quantum sensing. Or perhaps everything is equivalent to just having entangled input states, and there's no need to build a quantum computer for this kind of problem. We can just prepare some fancy entangled state. So that's the question we're going to try and answer today. Okay, that brings us to the outline for today's talk. So I already said that for this time-independent sensing problem, Heisenberg limit is sort of the fundamental limit. So we're going to need to consider a different problem in sensing. And it'll be sort of the next simplest problem, which is also like a very practically relevant problem. And that's what we call AC sensing. So AC sensing, fundamentally, is the problem of detecting a weak oscillating signal as efficiently as possible. So it's no longer time-independent signal, but it's sort of the next simplest thing. It's just oscillating at a single frequency. And so let's work through the workflow for an AC sensing experiment. So there are many possible sources of AC signals in nature. For instance, axionic dark matter is thought to couple in a way which can be captured by an AC magnetic field, AC field. Spectroscopy is an example of AC sensing. Even gravitational wave detection might be an example of AC sensing or time-dependent sensing. So there's some signal source. It'll be intercepted by a corresponding quantum detector of some kind. We'll do some degree of quantum processing, perhaps using a quantum computer. And then the output to this problem is just going to be a binary output or a detection output. So our goal is just to say whether or not there is a signal or there's not a signal. So for instance, for dark matter detection, as a first pass, we're just interested in detecting whether dark matter exists or whether the axion is the correct model of dark matter. And then we can worry about, estimating the mass of the axion later. Okay, so let's be a little bit more formal because ultimately, we want to be able to prove statements while also maintaining a level of physicality. So a bit more formally, we're going to be considering oscillating signals of the following form. So there'll be B of t is B cosine omega t plus phi, where these parameters B, omega, and phi are all unknown. They're unknown to us. And we're going to imagine that the signal couples to our sensors in some known way. So for instance, sum of poly z's is the canonical form in quantum sensing. And we're going to consider protocols of the following form. So in addition to our sensors, we're going to imagine that we have some small quantum computer. And our protocols can be expressed in the following form. So we alternate entangling gates between our quantum computer and our quantum sensors with time evolution under this unknown field. And then the figure of merit that we're trying to minimize will be the sum of all of these evolution times, so the total evolution time. And that's the thing that we're going to want to minimize. Okay, and you can even formally define a notion of an AC sensing problem. And that AC sensing problem will be parameterized by sort of two inputs. The first is what we call the sensitivity, or Bmin, and that'll be like, if the field exists, this is the minimum value of its field strength. And then the other parameter would be what we call the bandwidth, and the bandwidth will actually be an interval in frequency space. And we're promised that if the signal exists, then the frequency belongs to that interval. So you might ask, like, okay, like where did you get Bmin and delta omega? Like, how do you know these guarantees? Well, they might come from some prior theory, or they might come from prior experiments. We're just going to introduce these parameters to sort of formally characterize the difficulty of this problem. Because if you know nothing about the field, then of course it might take you an arbitrarily long amount of time to detect it. So that'll be our goal, is to detect AC signals with parameters that fall into this range. And our goal is to do it in the minimum time tau.
Richard, just to make sure, in this figure, the BT is separated by U1, U2, and UK, and so on. But what you really mean is that this signal is on at every instance of time, and sometimes you apply the U, right? When U is
Yeah, that's
applied,
right.
BT still exists.
Yeah, that's right. So we're working in the limit that your control gates, so the U1 up to UK, are much faster than the necessary sensing time. So we're imagining that, as a simple theoretical model, let's assume that these gates are just instantaneously fast. Now in practice, I'll actually, when I talk about our actual protocol, you won't need this. You can engineer everything just using some time-dependent Hamiltonian, which couples your quantum computer and your sensor. So you don't need this like super fast digital gates. But for the sake of simplicity, for now, let's like imagine this as a model, a theoretical model.
Yeah, thanks.
Of course. Okay, and I just want to take a moment here to emphasize that the sensing problem it's a practically useful problem because it really does connect to things like dark matter detection or spectroscopy. And it's a problem that has been considerably studied in quantum sensing. And I would also argue that it's a conceptually important problem because, so in quantum information theory, lately there's been a lot of interest in the theory of Hamiltonian learning. So if you have some many-body quantum system described by some Hamiltonian that's unknown to you, how do you learn what the Hamiltonian is? And we should think of this problem as maybe being a first step towards a theory of time-dependent Hamiltonian learning. And so if you're interested in generalizing this, I would argue that this is an important first step. And it's one where we'll already see some surprises. Okay, so as I said, this is like a real problem that people are solving in the lab. And so there are, of course, some existing strategies. So let me just say a little bit about how that works. And even before addressing this full problem, let's imagine a simpler situation where you actually know the frequency omega. So if you know the frequency omega, one thing that you can do is just apply pi pulses or X gates, which are resonant with this unknown signal. And if you do that, then in the toggling frame, or the sort of effective signal, is now going to be positive. So the effective signal, which is like conjugated by these pi pulses, is now it now averages to a non-zero value. And so you can just detect it using the simple time-independent protocol from before. And if you do that, we can sense a certain range of fields in time t. And so the sensitivity is, again, going to scale like 1 over t. But now, like our protocol will also have some bandwidth, which is some range of frequencies that it's sensitive to. So you're sensitive not only to frequency omega, but also some Fourier limited band centered at omega. And so the response will look something like this in frequency space. Okay, now what if you don't know omega? So that's the situation that we're interested in. If you don't know omega, then here's one simple thing that you can do. You can take your bandwidth, which is again like an interval in frequency space that we're interested in probing, and we can divide it up to a bunch of little frequency bins. And then we can just search one by one each of those frequency bins, and we can probe it with a pulse sequence that has a different resonance frequency. And so by sequentially searching across these multiple frequency bins, that's one way of solving this AC sensing problem. And that's more or less how it's done in the lab, by like a linear sweep over the bandwidth. Okay, so what's the performance of this strategy? We're interested in characterizing how long these strategies take. So the sensitivity and the bandwidth of each step are as before. But then we have to consider the total number of frequency bins. And the total amount of time is just going to be the number of bins times the time at each step. And if you combine all these relations above, you arrive at the following total scaling. And if instead you had multiple sensors, well, that just changes the sensitivity to become Heisenberg limited, and you get the following total scaling time. So you can believe me that if you combine these relations, you arrive at the following scaling for the total time. So it's linear in this bandwidth, delta omega, which is coming from the fact that you're sweeping across the bandwidth to detect the signal. Okay, there's sort of another way of visualizing this, which might be helpful. So far, I've been imagining that like delta omega and B min are parameters that are given to you as like a computational problem or a hypothesis testing problem. And your goal is to find the signal in the minimum time tau. A sort of dual perspective is that you might imagine that the total sensing time is fixed. Perhaps, it's the lifetime of a grad student, like 6 years or whatever. And you want to know what signals you can detect in your grad student's time as a student. And that's what this plot tells you. So it tells you for a fixed time what signals are detectable. And what you see is that by having entangled input states, your sensitivity improves. And so you can detect more signals. You can detect sort of everything to the upper left of the corresponding line. But the slope of this line is the same. Okay, so now, so far we've been like a little decoupled from our motivating question, which was, can quantum computing be leveraged to improve quantum sensing? So the goal now is to answer this question. And of course, we'll answer it in the affirmative. So that brings us to our first main result, which is that, indeed, there is a quantum computing enhanced sensing algorithm, which solves this AC sensing problem in the following total time. So if you compare this to the scaling on the previous slide, what we see is that we have a square root improvement in this factor delta omega over NSB min, which is like the number of frequency bins. And just a sort of technical note, this O tilde means that this scaling is correct up to logarithmic factors. So this is like a common notation in algorithms. And we call this algorithm quantum search sensing. That's just the name that we give it. And yeah, so this is our first main result. And then our second main result is that, in fact, this algorithm is optimal. So, if you consider any possible quantum computing enhanced sensing algorithm, even one that has an infinite sized quantum computer and can do infinitely fast gates, then even among all such protocols, they must take the following total time. So we call this lower bound the Grover-Heisenberg limit. And what it means fundamentally is that our algorithm is optimal, at least up to these logarithmic factors, which were indicated by the O tilde. So those are our two main results. And if we look at how this modifies the picture from before of what signals are detectable, well, what we see is that we unlock this sort of whole new region of parameter space. And note that this is a log-log plot. So this change in slope means that you can have like really sort of a dramatically more signals are detectable in the same fixed time. And furthermore, because of our lower bound, anything outside of this range is just impossible to detect. So this essentially pins down the question of what AC signals you can detect in a fixed time. Okay, good. So now I'm going to move on and say a little bit about how we actually achieve this result, sort of what our quantum computing enhanced algorithm is. But if there are any questions, now's a good time.
Previously, when I asked about the uh, generality of the Heisenberg limit, you said it's fully general. I guess you meant it's fully general if like the operation I can perform on the sensor is single qubit operations.
No, so that was a different problem, right? So that was the problem of estimating the strength of a time independent field or of detecting a time independent field.
I see. Uh-huh.
Now we're looking at a different problem, which is detecting oscillating fields. And
Uh-huh.
you might guess that the optimal protocol might just be some entangled initial state, so similar to Heisenberg limit, that you could achieve it just with some entangled sensors and you don't need a quantum computer. But actually, what we're arguing is that you do get an improvement from having a quantum computer. Um,
I see.
so
Uh,
that's
mm.
sort of the main
For
point.
for time independent signal, having a quantum computer doesn't help.
That's correct.
But then maybe one can further imagine there can be other types of sensing tasks which there are more hierarchies of improvement.
Yeah, I think that's a great question. We'll return to a little bit of this at the maybe at the conclusion of the talk.
Thanks.
Um, yeah, of course. But yeah, I mean, in general, you can ask the question, okay, I add in this resource. Does this resource change the landscape? Can I, solve problems that I couldn't before with this new resource? It might be an algorithmic resource. It might be some additional qubits. Um, and I think all of these questions are good. And I think it's important to understand the hierarchy of what's achievable in quantum sensing.
Yeah, very interesting.
Great question. Okay, great.
Sorry.
So, yes.
Yeah. May I ask the reason why you choose the total evolution time tau as the cost function here?
Oh, what else would you prefer?
Maybe the precision limit say the phishing information.
Good. So, yeah, that's right. So that's a good question. So, the perspective here is like I'm starting with the task that I want to solve. And so the task that I want to solve is detect this field. And you ask what resources are required to achieve that task. So quantum Fisher information by itself that's not a goal. The goal is not to get high quantum Fisher information. The goal is to sense with very high precision. It's to construct an unbiased estimator with very low variance. And that's why quantum Fisher information is useful. It's because it is a measure of how well you can perform at this task. So here I'm starting with the task, and then I'm asking what resources are necessary. And I guess my point is like, yeah, the goal is not high quantum Fisher information. The goal is solve this task. And the measure is not quantum Fisher information either. Like the measure should be how much entanglement you need, or how much time it takes, or how many gates you perform. That's my perspective, at least.
Okay, thank you.
Of course. And
So,
actually,
so,
we'll return to
uh,
quantum Fisher information later. We'll talk a little bit about it.
so in this sense, can I understand it as you kind of optimize the value of the time renormalized quantum Fisher information, something like
No.
that?
And we'll talk about this later. It's actually quite different.
Okay, thank you.
Yeah. So I would say it's not at all clear how to arrive at our results just by optimizing some quantum Fisher information looking quantity, or at least that's not how we approach the problem. And I'll say a bit about this later. Yeah.
Okay, I see.
Okay, good. So maybe it's best now if I describe our approach, and then maybe some of these questions will become a little bit clearer. So, okay, so recall our existing strategy, or what's sort of done in the lab now, or something similar to it. The essential punchline here was that if you search sequentially across multiple frequency bands, that's one way of solving this AC sensing problem. And the keyword here is going to be searching. And the reason it's a keyword is because, as you may know, quantum computers are useful for the problem of search, for searching an unstructured database. There is this algorithm known as Grover's algorithm, which has a quadratic speedup for search. But there are a number of assumptions that go into Grover's algorithm. And so the rest of this talk will sort of be about showing how you can make these assumptions compatible with our sensing setting. But this is sort of the high level motivation is we're going to reduce our sensing problem to a kind of computational problem and then leverage a computational speedup on our quantum computer. And you might imagine that this could be a more general framework for solving sensing problems. So we'll talk more about that later. But for now, we're interested in search. So, okay, before diving into this more, let me just take a moment and say, like, what do I mean by a search problem? So a search problem is a sort of very fundamental computational problem, which you can imagine as the following toy example. So given n identical boxes, which are totally nondescript, you can't tell the difference between them, the goal is to find one special marked box, which you might imagine like has a key inside of it. And classically, there's really nothing you can do except open these boxes one by one. So you open the first one, the second one, the third one, and then eventually you find the box that has the key inside of it, which we'll call K star, this marked box. And with a classical computer, it's easy to see that it's going to require a linear number of queries in general, because the key might be in the last box that you check. Okay, and then the very surprising fact is that if you have a quantum computer, it's possible to get away with fewer than linear queries. In fact, you can find this marked element with just square root n queries. And the algorithm that achieves this is called Grover search. Okay, but we should pause and ask very carefully, like, what does it mean to query quantumly? What is the notion here? And so this leads us to what's known as a quantum oracle, which is a sort of idealized model of computation. And that's the assumption in Grover's algorithm, is that you have access to this thing called an oracle. So what is an oracle? First of all, like in the quantum setting, the boxes are not boxes. We're going to encode them as different quantum states of our quantum computer. And then the quantum oracle is some unitary operator that sort of encodes the search problem. So if you feed it a state k of the quantum computer, it'll mark that state with a -1 phase if and only if k is the marked element. And then you extend by linearity so that the quantum oracle can act in superposition. So this is the thing which you query in Grover's algorithm. Okay, now what about for our AC sensing problem? We're not given this oracle, so we're going to need to somehow design or engineer it. We're going to need to engineer something that looks like the Grover oracle in order to leverage Grover's algorithm. Okay, so now instead of boxes, what we have are different frequency bins. So we can imagine, again, dividing our bandwidth into multiple bins and encoding these bins as different states of our quantum computer. So there'll be n states in total, and we'll encode those in our quantum computer. And then we need to engineer a sensing oracle which acts as follows. So it'll act, first of all, on both the quantum computer and the quantum sensor, because the quantum sensor is what actually interacts with the AC field. And then on the quantum computer, it should have the same action as the regular quantum oracle for Grover search. So it'll mark with a -1 phase if the frequency belongs to the kth bin. And the quantum sensor at the end of the quantum oracle should be unaffected. It should be returned to its initial state. And the reason is in Grover search, we're going to use this oracle multiple times. And so we want to be sure that the sensor is in the same state at the end of every oracle query. Okay, and then the upshot is, I didn't tell you how Grover's algorithm works, but it's some algorithm which queries this box to do search. If you just have this unitary, which we call the sensing oracle, then you can use it to run Grover's algorithm and solve this AC sensing problem with a square root of n speedup. And that's exactly the scaling improvement that we saw previously. Okay, so if you know a little bit about quantum algorithms, or if you knew about Grover search, then you might have been able to find your way to this place just sort of by following your nose. You might have deduced, okay, if we restructure AC sensing as a search problem, this is the kind of unitary that we need to have access to. But then you might get a little stuck because it's not at all clear how to engineer this sensing oracle. For one, quantum oracles they're very fragile. They're discrete objects and they act on many qubits. On the other hand, our AC signal, it's time dependent. It acts on a single qubit. It depends continuously on these unknown parameters, B, omega, and phi. And so it's just a priori not that compatible with this framework of quantum oracles. And so that'll really be the challenge, is how to engineer such a black box, such an oracle. Okay, and just to sort of drive home the point here of why the sensing oracle is maybe a difficult thing to realize in practice or to engineer, I'm going to point out a couple of key differences between the sensing oracle and conventional quantum sensing. So the first is that our sensing oracle needs to sense in superposition. So if you remember for conventional quantum sensing, your protocol is sensitive just to a single frequency. So there's response at just one frequency. Instead, in our setting, we need to engineer a sort of conditional response of the sensor. So conditional on the state of the quantum computer, we want the sensor to have some response. And this by itself is actually not too hard to engineer. One way that you can do it is just by doing the conventional sensing sequence conditioned on the state of the quantum computer. So just perform controlled X gates instead of X gates. But this is actually not going to be enough because of the second key property that the sensing oracle needs to have, which is that it's digital. So to motivate this, let me again return to the conventional example. So I said before that the effective signal, or in the toggling frame, the signal has a positive mean value, and therefore you can detect it. But this is like not quite right because I've assumed a particular phase relationship between the signal and our pulse sequence. And if the phase is shifted, then it's possible that the resulting signal still averages out to 0, and then that's not detectable. And this is an issue in our setting because the phase of the field is actually not known. And I mean, this is just one example. It's possible to get around this sort of phase issue in a different way. But what it points to is the fact that, really the response of the sensor, it depends very sensitively on all of these parameters, B, omega, and phi. And that's by design, because in conventional sensing, you want a very sensitive response to small fluctuations in these parameters because you're trying to detect those parameters. By contrast, our sensing oracle should have a very discrete or digital response. So for all values of the phase and for all values of the strength greater than the sensitivity, we need to have the exact same response of the sensor. It should be exactly a -1 phase flip. Okay, and this is what we call digitization. It's the process of mapping the left-hand side to the right-hand side. And I want to argue that this is really a critical part of interfacing quantum sensors with quantum computers, that this is a problem that you would have had to solve in many different settings, or if you're trying to interface these two. And we're going to provide a sort of toolkit for completing this. Okay, so now I'll dig in a little bit into the construction of the sensing oracle. But first, are there any questions so far? Okay, if not, let me move on. So there will be sort of 3 main ingredients in building the sensing oracle. The first will be phase agnostic sensing. The second will be sensing in superposition, as I mentioned already. And then the third will be nonlinear signal processing. And each of these ingredients is going to come together to engineer this discrete sensing oracle. Okay, good. So first, let me talk about phase agnostic sensing. So before engineering the general sensing oracle, let's start with sort of an intermediate goal, which is to get, again, a conditional response of the sensor, a conditional phase rotation of the sensor. But now, I'm not going to demand that these angles be exactly pi or 0, so phase of -1 or +1. But I'll say that it suffices to have a rotation angle which doesn't depend on the phase phi of the magnetic field. And the reason why this is a reasonable intermediate goal is somehow the time dependence of the field is captured by this phase. Because if you look at the field at a different time, the only thing that's different is the value of the initial phase. So if we can engineer a response that's insensitive to this phase phi, that'll be sort of a good first step towards our general goal. Okay, and the key idea to engineer this is very simple. It's just the AC Stark shift. So AC Stark shift, if you're not familiar, is a very fundamental principle, quantum optics, first year quantum optics. And it goes as follows. So this is our original Hamiltonian coupling to the 2-level sensor. I've written it in the X basis, but could be any basis that you like. Let's imagine that we add some time-independent detuning, which is controlled by us, to the Hamiltonian. And if you do this and you analyze the dynamics in the rotating frame, so the frame that's rotating at frequency omega, you get the following effect of Hamiltonian, which is now time-independent. And this Hamiltonian is a very nice feature, which is that its eigenvalues are actually independent of the phase phi. So this is a step in the right direction. We wanted to engineer insensitivity to the phase phi. Here we have an effective Hamiltonian, which is insensitive to the phase. But there's a little bit of an issue. If you look at the dynamics under this Hamiltonian, it's time independent, single qubit, so you just have Larmor precession. And the angle of precession is independent of phi because the eigenvalues are independent. But the actual axis of rotation depends on phi. I mean, you can see it explicitly in this effective Hamiltonian. And that means that the final state will also depend on phi. And we wanted to get rid of this dependence. But there's a fix to this. And the fix is that we can just adiabatically turn on the coupling to the magnetic field. So instead of just turning it on like all at once, we're going to adiabatically turn it on and off. We start at 0, we ramp it up to 1, and we're going to ramp it back down to 0. And if you do this, well, initially, when chi is 0, the Hamiltonian is just along the z-axis, and so your state is polarized along z. Then as you slowly turn on the field, the axis of precession it'll move out in some direction dictated by phi, but the state will just follow if you ramp slow enough. And then when you ramp back down, the state will return to its initial state, the 0 state. And if you do this, then the final state is phase independent as well. And so this has basically engineered our phase independent response, or our phase agnostic sensing. Okay, so that's how you do this all for a single qubit. The next ingredient is to do this conditional on the state of the quantum computer. Remember, we're trying to engineer a conditional response. And at the level of theory, that's very easy. You just let this detuning depend on the state of the quantum computer. So you can engineer a conditional detuning, at the level of quantum algorithms. You just write it down, you do it. In practice, there's actually a pretty easy way of attaining this just with Ising couplings between your computational qubits and your sensor qubits. And I'll talk a little bit about that later. But for now, this is just an easy change. And then let me just say one more word about these phase angles theta k. We don't need to know exactly what they are because we don't know like B and omega, but we will need one property of them. So first of all, like these angles are just the dynamical phase under this evolution. So first or second year quantum mechanics, the dynamical phase is just the integral of the time-dependent eigenvalue. And to first order, it looks like this. And these dynamical phases have a nice property, which is that this angle is largest when k is equal to k star. So when the value of k is actually the value of the bin that contains the frequency. And well, why is that? So this detuning, it's the detuning between your control and the true signal frequency. So that's smallest for k equals k star. And that means that the phase response is largest for k equals k star. So that's what we know. We know that the phase is largest in the marked state, and it's smaller in all the rest. And it turns out that's all we're going to need for this next step. Okay, so final step to engineer the sensing oracle, nonlinear signal processing. So let's remember first the spirit of this digitization idea. It was to map a continuous or linear response of the sensor to some discrete nonlinear response. And so the question is, how can we engineer these nonlinear transformations quantum mechanically when quantum mechanics is fundamentally like a linear theory? And the good news is we didn't need to answer this question by ourselves. It's sort of already been answered by this framework known as quantum signal processing. And so quantum signal processing, if you don't know it, it's a very powerful framework for designing quantum algorithms. It's very, very interesting. You should take a look at it. But let me just tell you the very basics first for the purposes of this talk. So the basic setting in quantum signal processing is you have some signal unitary, which we're going to say is a z of theta. So that's a rotation about the z-axis by angle theta. And then we have some optimized control unitaries, which we're going to interleave with the signal unitary. And the goal is to engineer some rotation by an angle f of theta, where f of theta is in general some programmable nonlinear function. And quantum signal processing allows you to do this for your favorite choice of nonlinear function. And so, the problem just becomes choosing the right f, right nonlinear function f, and then figuring out what the corresponding control unitaries are. So the right choice of f in our case, we're going to figure it out as follows. What we have is the following unitary, where the response theta k star is largest, so the phase angle is largest for the marked bin. And what we want is a setting where the phase angle is exactly pi in the marked bin, so we get a -1 phase, and it's exactly 0 otherwise. So basically, we just want to amplify this difference. We have the theta k stars, it's already larger than all the rest of them. We just want to amplify this distance, this difference. And the way we can do that is by choosing f to be some approximation to a step function. So if we choose f as an approximation of the step function, we can do quantum signal processing to exactly engineer the sensing oracle. And that's the full construction of the quantum sensing oracle. Good. So that was like a lot of information. Hopefully not too much detail, but that's basically the full construction. So now you know how it works. Next, I'm going to talk a little bit about some broader perspectives and possible experimental implementations. But maybe now is a good time for any questions in this last section.
I have a question. So I suppose when one implements this protocol, there will be all kinds of imperfections, like the step function is not that step, this and that. How do they affect the error?
Yeah, I think this is a great question. So some degree of robustness you can build into the algorithm for free, because in some sense, many of these like digitization strategies, they're sort of meant to engineer robustness. So you get a certain amount of robustness either to imperfections in your control or to imperfections due to like noise. You can get a certain amount for free. But the general question of like, how does our protocol respond to noise or imperfections in your control unitaries? I think a detailed analysis of that would be important, but yeah, I don't have maybe like exactly the answer there.
But your theorem too is a general bound of how long the time it takes.
Yes.
That doesn't care about the details of the protocols. It doesn't care about any imperfections.
That's right. So that's even if the protocol is perfect, it needs to take that much time.
Mhm.
I mean, if the protocol is imperfect, then of course it'll take more time.
Yeah. Thanks.
So the lower bound, it's even for these very idealized perfect protocols. Yeah. Okay, great. So now let me talk a little bit about what we call computational sensing. So I've claimed so far that like this is a qualitatively different approach with enhancement arising from computation, quantum computation. And I should sort of justify that claim because the whole motivation was to, just to find some problem for which having a quantum computer helps you in quantum sensing. And I should justify that claim. So the way that we do that is by considering some sort of restricted models of quantum sensing, which resemble more the conventional setting in quantum sensing, but lack some of the ingredients essential to quantum computation. And for these different restricted models, we can actually prove lower bounds on the amount of time that such a protocol would take to solve the sensing problem. So the first restricted class of protocols that we consider are what's called QFI-based protocols. So there was a question earlier about QFI or quantum Fisher information. If you don't know what it is, that's okay. But QFI is sort of like the conventional measure of performance in quantum sensing. Large quantum Fisher information is often equated with better performance for quantum sensing. And so one reasonable approach to solving this AC sensing problem might be to design a protocol which maximizes the quantum Fisher information, this quantity, for all frequencies in the bandwidth delta omega. That might be like a reasonable approach if you're coming from quantum sensing perspective. But our first main result in this area is that, in fact, any such protocol is fundamentally limited, and it must obey the same lower bounds. It must obey the same scaling as the conventional protocol at the beginning. So it cannot attain this like stronger result, which our algorithm achieves. And so this is somehow like a little surprising because quantum Fisher information we think of as being the measure of performance in quantum sensing. But here we show like not only does quantum Fisher information not capture the result of our sensing algorithm, but it's actually like orthogonal to that result. So if you have like large quantum Fisher information across the bandwidth, then you must be sort of bad at solving our sensing problem. And so what it tells you is that fundamentally a non-perturbative approach is necessary, and that at least for this problem, the QFI is of limited use. Okay, we also consider another class of sort of conventional or classical sensing protocols, which we call classical signal processing. And these are protocols which sort of like capture the power of classical linear signal processing. So there's one way that you can think of them is these are protocols that are equivalent to applying some filter function to every single sensor. So some general time-dependent filter function, which you can imagine is being realized by some classical signal processing transformation. And our result here is that, in fact, any such protocol must obey the same lower bound as before. So, in particular, the protocol that I started with at the beginning of linearly scanning across this bandwidth by using like pi pulses, that can be expressed as one of these classical signal processing protocols. And what we show is that actually like that protocol is optimal among these classical signal processing protocols, and it fundamentally cannot achieve our result. And what this tells you is that like a nonlinear approach is going to be necessary. Okay, so this was some understanding of the role of computation in the performance of our algorithm. And now I'd like to sort of conclude the technical part of my talk by saying a little bit about the possibility of near-term experiments and what the actual requirements would be to see a quantum computing enhanced speed up in practice. But any questions on this last section before I move on? Okay, let me go ahead as we're running a little low on time. Okay, so what are the actual experimental requirements for running our algorithm? I mean, I've described something that's like maybe a little bit complicated. We have this sensing oracle, and I imagine that you could do the sensing and superposition. What are the actual requirements to realize this in practice? Well, it turns out that they're pretty minimal. So you're going to need arbitrary rotations of your sensor. So let's imagine that's just one sensor. We need to be able to do arbitrary like X and Z rotations to do QSP, quantum signal processing. We're only going to need global single qubit computational rotations of the computational qubits. And that's for Grover's algorithm. You need to be able to do this. But it's like the same single qubit unitary applied to every computational qubit. Kind of simple. And then finally, we need some way of coupling our quantum sensors to our quantum computer. And it'll turn out that Ising interactions between them are sufficient. And why is this the case? Let's focus in on that. So let's look at the following Hamiltonian describing Ising interactions between a single sensor, ZS, and NQ computational qubits. It looks like the following, where Ji are the Ising couplings. We can actually rewrite this in the following form, where now the index K sums not over the spatial index of the computational qubit, but all the possible 2 to the NQ states of the computational qubits. And these strengths, omega K, are like the signed linear combinations of all the Ising couplings. And so, this is the resulting Hamiltonian from Ising interactions. And what you see is that this is like exactly the kind of Hamiltonian that we needed to do a conditional detuning of the quantum sensor, which is what we need to do the sensing and superposition. And so, there's another way of looking at it, which is just like the energy diagram. You can imagine that what we have is a conditional shift of the energy of our sensor. And then the mark state K star will just be whatever state is such that this gap is closest to the true frequency omega. So Ising interactions are enough. And in fact, we can push this a little bit farther and do some detailed numerical simulations of a proof of principle experiment of our protocol. So we consider Nitrogen Vacancy Center platform, which is like a leading platform for quantum sensing experiments. In this platform, you have 2 kinds of qubit degrees of freedom. One is this NV electron spin, which is a very good sensor for magnetic fields. And then the other spin degree of freedom is a long-lived nuclear spin of nearby C13 nuclei. And this long-lived nuclear spin can be used for computation. We solve a slightly simplified version of the problem to remove some of the baggage of like quantum signal processing. And in this slightly simplified problem, you imagine that sort of B and phi are actually known, and omega belongs to some discrete set, not a continuous interval. And the reason for this is just we want to capture like the sort of quantum computing enhanced aspect without all of the additional apparatus or details. And in this setting, the sensing oracle is quite a bit simpler than the construction that I presented. It's just a 2 pi rotation on the correct frequency omega K. And we do very detailed numerical simulations with realistic values of decoherence rates and coupling strengths. And we quantify our improvement over conventional protocols by what we call an improvement factor, which is just the ratio of the conventional time to our quantum computing enhanced time. And I'll just flash these results, but the punchline is for sort of realistic values of decoherence, coupling strengths. We'd expect about like a factor of 4 to 5 improvement in the total sensing time. That's what's depicted on the left-hand side. And then on the right-hand side is sort of like an optimistic prognosis for the future. If you had improving T2, improving number of computational qubits, what sort of gains that you might see. So this dotted red line is like, that's the exponential speed up from Grover search that you would expect. Okay, that brings me to the end of the technical part of my talk. Let me just wrap up with a little discussion and outlook before taking some questions. Okay, so what's next for quantum computing enhanced sensing? Or what are sort of like the key perspectives or ideas, in my view? One perspective that I really like on this work is the idea of treating nature as a quantum oracle. So this quantum oracle model, it's one of the first things that you learn in a class on quantum computation or quantum algorithms, but it's somehow very frustrating, like because you don't know who gave you this quantum oracle or how you would actually realize it in practice. And you imagine that you have to access this oracle in like a black box way, because if you could look inside the details of the oracle, then you would actually know the solution to the problem that you're solving in many instances. And one perspective on our work is that this is a way of unlocking the black box by realizing oracular dynamics just from natural physical Hamiltonian dynamics that occur in nature. And one of the main perspectives of our work is like quantum sensing naturally translates to this quantum oracle model. And that leads to a very simple question, which is, there are larger oracle speedups in quantum computation, larger than the quadratic speedup of Grover search. Can we leverage these speedups to get even larger metrological gain? So that's one open question. And then another has to do with designing what we call logical quantum sensors. So, our classical devices couple the sensors all the time. So, I mean, I'm looking at you through a video camera and I'm typing on my keyboard. These are classical sensors which interface with our classical computer. But there's a little bit of a tension between error correction and sensing, because in error correction, you want to be resilient to noise, and in sensing, you want to be sensitive to weak fields. And so there are some sort of pessimistic no-go results about the relationship between quantum sensing and quantum error correction. And one question is whether or not some of our digitization techniques might be useful here, whether they could beat some of the conventional wisdom on the possibility of error-corrected sensing. Okay, that's all for me. Thanks so much for your attention, and I'd be happy to take any questions now.
Okay, Richard, thank you for the very interesting talk. Questions?
Yes, may I ask one question?
Please.
Yes, okay. Thanks, Richard, for really exciting results. Congratulations to you for this excellent direction. So I hope I understand correctly. Okay, let's say you want to reach a certain precision of omega. Okay, and I can view this as Fisher information about omega. And your question is how much time you need to reach that precision, right? And then you're using quantum search algorithm to show that, hey, you can beat the naive protocols or all the protocols that we are aware of by extending this quantum search algorithm. Okay. Now, there's one puzzling here. You mentioned that this approach is orthogonal to quantum Fisher information approach. But think about this, okay? Suppose I know what kind of Fisher information I need to reach that precision. In principle, there are many possible ways for me to generate that quantum Fisher information. It could be, I could be whatever function of t. In some cases, I can imagine we could think about a scenario where quantum Fisher information can exponentially grow with time. And in that scenario, the time I need might be shorter than what you discovered using quantum search algorithm. So I was wondering how come you can prove this is the best you can do using your protocol? Yeah,
great.
That's my question.
Yeah, that's a great question. And so, actually, on the one hand, the answer is very simple. It's that we're not solving a frequency estimation problem. So somehow, like the fact that we can leverage quantum computing in this sense, in this setting, is tied very intimately to the fact that we're solving a detection problem. So our problem was not to estimate the frequency to very high precision. If you do that, then the performance for that problem is characterized by the quantum Fisher information, this estimation problem. But what we argue in our work is like, okay, we do care about estimating things like frequency or field strength to very high precision, but as a first pass or as a first initial question, what we really care about is whether or not the signal even exists. So we want to detect dark matter. We're curious if the axion is the correct model. We want to just solve this detection problem first. And so we frame things as like a hypothesis testing or detection problem. And from this perspective, it's maybe less surprising that quantum Fisher information is not the right measure of performance.
Right. Yeah, now I understand better. Yes.
Yeah.
So
So
you
like
are trying to answer. Yeah.
certainly like having a high quantum Fisher information would be sufficient to solve this problem. But what we show is that it's kind of overkill. And if you have high quantum Fisher information, that means that you're like wasting some
That's
information.
right. Yes.
So you must do worse at this testing problem. And so that's, yeah, it's not, we're not saying like, oh, quantum Fisher information is dead. We should never care about it. That's certainly not the case. It's just not the right metric for this problem.
Excellent. Wow. Thanks very much. Yeah. Now
Yeah,
I will go
thanks for
back
your
to
question.
read
It's
your
very
paper.
insightful.
Yeah.
Okay. Yeah,
Thanks.
that's a very, very insightful question. Yeah. And yeah, and I
Yeah,
hope, I mean, I hope that other people will maybe take this perspective that, I mean, quantum Fisher information is the right quantity for some problems, but not for all problems. And if you're studying a sort of hypothesis testing task, I think there's a lot of room for exploration there and seeing how these other resources might be useful. We found these results pretty surprising at first. So
Wonderful.
other questions?
Yeah. Hi, Richard. I have a question. Thank you very much for the very nice talk. So my question is, how can we combine this protocol with, say, the traditional quantum precise measurement method? So in my understanding, I think in traditional precise measurement protocols, we have to increase the number of n in our measurement. And if so, then I think the more measurement qubit you have, then the more difficult it will be for us to control the measurement qubit in a quantum computer. Then what do you think about it?
yeah, that's a very good point. So there may be like a few aspects that I can share about this. So the first is, if you have multiple sensor qubits that you can prepare in an entangled state, you should still do that. You should still prepare your sensor qubits in some entangled initial state, and that will still buy you an improvement in sensitivity. So you can get a Heisenberg limited improvement in sensitivity. That's why we call our fundamental limit like Grover Heisenberg.
Yeah, right.
Because you can still have entangled sensors. Okay, but your point is maybe if you have multiple sensors, it might be harder to interact them with a quantum computer. Is there some trade-off here? I agree. Like in practice, I think there certainly would be a trade-off. If you have entangled sensors, then pretty generally that decreases your coherence time linearly with the number of entangled sensors. This is a good practical consideration. One like final comment is if you imagine that you just have a fixed number of qubits, and they could be used as either sensors or computational qubits. Like, how should you allocate them? You should definitely allocate them towards computation, not towards sensing, because if you just look at the scaling of our result, you get a sort of exponential growth in the number of computational qubits because the bandwidth, this bandwidth is like exponential in the number of computational qubits, but you get only a polynomial improvement in the number of sensors. So if you somehow like have a choice of how to allocate your qubits as sensors or computer qubits, you should always make them computational qubits. And then maybe, you can maybe error correct them more easily or something like that. But yeah, I think it's the correct answer to the question is probably very context dependent. So hard to give a general answer, but these are a few reflections that I have.
Oh, thank you very much. And do you have an understanding for the scaling behavior of n and t in, for example, even in a certain problem?
Sorry, could you
The scaling
repeat the question?
behavior I mean maybe the precision of the precision of n, the number of sensing qubit, and t, the time. Do you have a scaling behavior estimation?
I'm not sure I understand your question.
Yeah, I'm asking if we know the behavior when I scale up the number of sensing qubits and the time.
How much the
We-
sensitivity improves?
Yeah.
Yeah, that's characterized by our results. So we wrote our results as like sensing time equals some function of the sensitivity and the bandwidth and the number of sensor qubits. You could rewrite that and write the sensitivity in terms of the sensing time and the number of qubits, blah, blah, blah.
Then this is case dependent, right?
It depends on how much resources you have, I suppose.
Oh, okay. Thank you very much.
Yeah.
Yeah, go ahead.
Yeah.
I have a question. What's the intuition behind your theorem 2?
Oh, yeah, the lower bound proof.
Yeah.
Yeah, so yeah, I didn't talk about that so much in this talk. But it's it's a rigorous theorem that one can prove. The proof sort of has two parts. Part of the proof is inspired by the proof that Grover's algorithm is optimal. So, I talked about Grover search, which gives you a square root improvement for search. You might ask, like, could you do even better with a quantum computer? Maybe you could get fourth root of n. It turns out you can't, and that Grover search is optimal. And the reason for this is basically you get a linear accumulation of the amplitude of the correct state in Grover's algorithm, as opposed to a linear accumulation of probability. And because probabilities are the squares of amplitudes, that leads to like square root n total time. So that's sort of the intuition. And there's like a speed limit on how fast the amplitude can accumulate. And so that's why Grover search is optimal. So that's one part of our proof for the lower bound. The other part has to do with you can sort of divide the times. You can divide into two time scales. There's a very short time scale and then a long time scale. And then the very short time scale you have to handle separately. And then once you know that the performance of your algorithm is bounded for very short time scales, you can like bootstrap this using the idea from the Grover lower bound. So I'd say the best intuition is like the square root comes from the Grover search, like how Grover search is optimal. And the intuition for that is that amplitude accumulates at most linearly.
Thank you.
Sure. Good question.
Other questions?
I have a question about nonlinear processing in Hilbert space. Could you give an intuitive picture of what it means?
Like this idea of quantum signal processing?
Yeah,
Yeah.
nonlinear processing. Yeah.
Right. So yeah, I guess quantum mechanics is still linear, right? It's still linear theory. I'm not violating that. But yeah, what this idea of quantum signal processing allows you to do is if you have some unitary that depends on some angle of rotation, and you're interested in rotating by some nonlinear transformation of that angle, then you can do that using quantum signal processing. And if you know anything about like composite pulse design and NMR, like that's maybe a place for some intuition. Does that help at all?
Okay. Thank you.
Sure.
Any other questions? Richard, you went to Harvard as an undergraduate student. Maybe at Harvard we were trained to wait for 7 seconds every time when I say, "Are there any other questions?" I just waited for 7 seconds. So it seems there's no more question. Okay, thank you again very much for the very interesting and exciting talk.
Yeah, thanks everyone for your attention and for your engagement. Really great questions, and it's nice to meet all of you.
Yeah.
Thank you.
Bye.
Thank you, Richard. Bye-bye.
Yeah, I hope you have a nice day.